Okay, let's look at 1.8 absolute value equations and inequalities. So we're just going to remind you the definition of the absolute value of a number. And the absolute value of a number is denoted by that number, so we're just saying let A be any real number. And when we put A between two vertical bars, that denotes the absolute value, and it's defined to be this. It's just the number itself if A is greater than or equal to 0, but it's minus that number when A is less than 0. So for example, the absolute value of minus 5 is equal to minus 5, which is equal to 5, because minus 5 is less than 0. And the absolute value of 5 is equal to 5. The thing to remember about absolute values is they are always positive or 0. Let's take a kind of visual look. That's the conceptual definition. Let's look at a visual definition. Hold on just a second. I gotta plug in my writing tablet here. Okay, now I have control. So let's just draw the number line. And remember, the number line extends on forever and ever, all the way to infinity and minus infinity. Now these aren't actual points, it's just, these are just symbols to indicate it continues on. And we're going to need some demarcation where the 0 is. So I'll literally just put 0 about in the middle. So if I say that this is 5 on the number line, then I'm going to need to mark the same distance. I'm eyeballing it here, so you'll just have to excuse me if my eyeballing of distance does not suit you. So this is minus 5. So the absolute value of minus 5 is just equal to 5. And the absolute value of 5, of course, 5 is positive, is equal to 5. So on the number line, what we have is that 5 is literally the distance between 0 and 1. And it's the same distance, I'm talking about distance now, between minus 5 and 0. So another way to conceptualize the absolute value of a number is to consider its distance back to 0. And distance is always positive or 0. It's in another interesting note, an interesting thought question for you. When is the absolute value of A equal to the absolute value of minus A? That's always true, right? I just told you the answer. So let's go on and look at some rules for solving equations and inequalities that involve absolute values. Now, if you had intermediate algebra, the first two rows of this table right here you should be familiar with. This says if the absolute value of some number x, and here it's important to remember that in this case x stands for, I probably should have used an uppercase level here, but in this case, for this table, x stands for any unknown number, so the regular meaning of x, or an algebraic expression. So what would be an algebraic expression? Well, it could just be any constant number, but something like 2x minus 5, that's a linear polynomial in the variable x, or 5w minus 1/2, etc. So x here is standing for any algebraic expression. Clearly x just by itself. And if you want, maybe I'll go back and edit this at some point. Consider the x here as some capital X. And I just want you to know that that can be actually just a variable. It's some unknown, right? The value is some unknown quantity. The value of 2x minus 5 is another unknown quantity. You don't know what the quantity is unless you know the value of x. 5w minus 1/2. That's another unknown quantity. We can't know what the unknown quantity is unless we know the value of w. So using x right here to stand for an unknown quantity is conceptually consistent with what I just said. So if the absolute value of x is equal to some number k, then we have that x is equal to k, or x is equal to minus k. And our solution set is a set with two numbers. This is not an interval. This is a set with two elements, minus k and k. If we have the absolute value of x equal to minus k, absolute value of k, then x is equal to k, or x is equal to minus k. So really, row 1 and row 2 are really easy. Notice the difference. They're dealing with equalities because we have an equal sign there. Now in rows 3 and 4, we're dealing with inequalities. And we have many different types of inequalities, and I've just chosen the less than or greater than as the generic inequality sign. So just to remind you, we have greater than, less than, greater than or equal to, less than or equal to. Now the direction here is important. So you can replace the less than with the less than or equal to. You can replace the greater than with the greater than or equal to if you remember the following. If A is less than or equal to B, let me just actually start this out. If A is less than or equal to B, that is shorthand for two different statements. That means, first statement, A is less than B, or A is equal to B. So this combines two types of statements. One is an inequality and one is an equality. And A is less than or equal to B if one or the other of these are true. I think in our exercises we don't see the absolute value of x is less than or equal to k, but if you did, you would have to evaluate this or this, and you have the rules to do so given right here. So let's go on and look. So let's look at the absolute value of a number as less than k. So here I just give you the answer. I mean, this is the equivalent form. So this equation, this inequality right here is equivalent to this, to stating that x is between k and minus k, and its solution set in interval form. Notice these are curly braces, those denote a set. These are open interval symbols. So this is an interval. This contains exactly two numbers. If minus k is not equal to k, which only happens when k is equal to 0, this interval contains an infinite number of elements. If k was equal to 0, then it would contain no elements. You don't have to worry about that last part. It may have thrown you off. When it becomes important, if it becomes important, I'll talk to you about it. So let's look and see what this is telling us on the number line. That's what I was wanting to do. So here's our number line again. and I'm going to say that's about dead center. And again, I'm going to say k is here and minus k is there. So let's just look at an actual number. I'm going to say this is 5. I'm going to say this is minus 5. So what does it mean? What kind of values of x, when I take its absolute value, is going to be less than 5? Well, let's look at 3. Well, the absolute value of 3 is certainly less than 5, and the absolute value of minus 3 is certainly less than 5. And the same is true of any number that I might choose, getting closer to 0, including 0 itself. The absolute value of 0 is 0, and the absolute value of 0 is certainly less than 5. As a matter of fact, this actually occurs all the way until you get right up close to 5. But since we want it to be less than or equal to 5, it's this entire interval in here. So the solution set for values of x are given by what's in red. X is equal to whatever is in this interval. And hence, reading off our interval notation, we have that x, remember the symbol is in, the symbol means is an element of. I will use it on occasion because it's just shorthand. You saw how long it took me to write is an element of, so we just read that. We don't try to pronounce it as E or anything like that. We just simply say is an element of. Or if we want to be really verbally lazy, we just say in. X is in, and what follows is always a set. X is in the open interval from minus 5 to 5. So I just visually explained what's going on in row number 3. So if the visualization helps, that's good. So what about the visualization of the next one? The next one is non-intuitive. What happens if the absolute value of x is greater than k? Let's try to use this same drawing rather than me drawing another line. So let's look at a particular example and consider the case when the absolute value of x is greater than 5. Well, clearly none of these values in this interval here will work because those satisfy the equation that the absolute value of x is less than 5. But if I choose x equals to 6, its absolute value is greater than 6. And if I choose x is equal to minus 6, its absolute value is greater than 5. So in this case, we have the following interval is our solution set. Starts at 5 but doesn't include 5, and starts less than 5 but doesn't include less than minus 5 and doesn't include 5. So in this minus 5. So in this case, that's the solution set for here. The solution set for here is going to be x in, well, let's write the interval. Starting here, this goes to minus infinity, this goes to plus infinity. We start at minus infinity. We get all the way to minus 5. Then we come over here and we start at 5 and we go all the way to plus infinity, and we take the union of these two sets. So in this case, we have a nice compact way to write the solution set. Here we literally have to use, since these two sets are separated by this area demarked in red, I have to take their union. And just a little review about the union of two sets. So let's make union and intersection. So let's draw a set A and a set B, a set A and a set B. So I'm just going to use the same color. I'm getting lazy. That's A and this is B. That's A and this is B. So anything, this is just a visual representation, because I know some of you are visual learners and it helps conceptually. So anything within the boundaries of the salmon colored circle is in A, and anything in the boundaries of the purple circle is in B. So the intersection of A and B is denoted this way, and this means intersection of A with B, although sometimes they'll say A and B, is simply every element that is in A and in B. So the key word here is and. Visually, that is denoted by this area right here. On the other hand, if I have A and B and I take their union, so union looks like a U, but it doesn't have the little bitty down leg. So that's the union of A with B. Well, the union is anything in A or anything in B. Any element in A or any element in B. So clearly that includes the intersection, but it also includes that and that. So notice visually you can see that the union of two sets is almost always a larger set. If the two sets are distinct, it's always a larger set as long as B is not empty. The intersection of A and B is a smaller set than A or B, and indeed it could be that, let me give you this possibility right here. Oh wow, interesting. That A and B don't overlap at all, in which case their intersection would be the empty set, but their union, on the other hand, would be what's contained in both sets. So some interesting things to keep in mind. I don't think they're going to play an important role for this particular problem, but it's something to keep in mind in the future, because those concepts of set, intersection, and union are very important in math. So let's do two really simple problems that are going to use our first two rows. So we'll just label this as 1a. So I have the absolute value of 5 minus 3x is equal to 12. So what that means is the following. 5 minus 3x is equal to 12, or 5 minus 3x is equal to minus 12. So now all we have to do is solve these linear equations. So I have minus 3x is equal to 12 minus 5, because I moved the minus 5 over. So that gives me not minus 7, but 7. So I divide through by minus 3. And that gives me x is equal to minus 7/3. Over here, I take the 5 to the other side, and it becomes negative. So I have minus 3x is equal to minus 12 minus 7 is minus 17. I divide both sides by minus 3. So I get x is equal to minus 17 divided by minus 3 is the same thing as 17 divided by 3. So remember, x is equal to this or x is equal to that. So we have two separate values for x. So our solution set is a set, which is not an interval, but a set that contains exactly 2 elements. For the next one, we're going to do this one. Well, this one, problem number B, uses row number 2. So we have the absolute value of 4x minus 3 is equal to the absolute value of x plus 6. So that implies that 4x minus 3 is equal to x plus 6. And here, be careful. We write or. The 4x minus 3 is fine. But here I sense a possible error. I can't put the minus just right there. It's minus everything on this side. A common error at this point is students will write 4x minus 3 is equal to minus x plus 6. But minus x plus 6 is not equal to minus in parentheses x plus 6. This will give you the wrong answer. It's a very common mistake. So remember, the entire thing is negated, not just the first term of a sum. So now let's just solve these. So I'm going to take the x over here. So this simplifies to 4x minus x is equal to 6 plus 3. You should be able to easily verify that. 4x minus x is 3x. And 6 plus 3 is 9. How nice of them. We divide through by 3. And that gives me x is equal to 3. Over here, we have to do distribution on the right-hand side first. This is the same as minus 1 times x plus 6. So minus 1 times x is minus x. Minus 1 times 6 is minus 6. That's the reason minus x plus 6 is wrong. It's really minus x minus 6. Now I'm going to move the minus x over. That's going to give me 4x plus x. And I'm going to move the minus 3 over, and it becomes plus 3. So this gives me 5x, and this gives me minus 3. So I'm going to divide both sides through by 5, and I get x is equal to minus 3/5. So again, this is an equation. I have two different values that satisfy it. That's my solution set. It's not an interval. This is a set that contains two elements. An interval always contains either no elements at all. For example, the interval from minus 5 to minus 5 contains no elements. It's equal to the empty set. Now, as long as a and b are different numbers, that interval contains an infinite number of elements. An infinite number of elements that is so large that is mind-boggling. No matter how close b is to a, it still contains a very, very large classification of infinity, an infinite number of elements. I'll stop right there, but that's where math gets really non-intuitive and interesting. Georg Cantor discovered that way back in the early part of the 20th century. Mathematicians didn't want to believe it. They attacked his proposition. Of course, he was true, but I mean, he was exactly right. He eventually died in an insane asylum. One doesn't know if it was because of such profound thinking, or it was a genetic factor, or schizophrenia, who knows, or just the fact that his fellow mathematicians didn't believe him. But if you're curious, Georg Cantor, I think he was a Hungarian mathematician. Oh, when you get into that area of math, it's just absolutely beautiful. So here we have a row 3 problem. 2x plus 1 is less than 7. So that translates to the following. 2x plus 1 is less than 7, or is less than minus 7. So this is a compound inequality. So this literally means that our solution set is going to satisfy two inequalities. It's going to be the intersection. It satisfies the inequality minus 7 is less than 2x plus 1, and that denotes setwise intersection, 2x plus 1 is less than 7. Now you could find the solution interval for this and the solution interval for this, and then take their intersection. But thankfully, there's an easier way to do this. So I'm going to rewrite this down here. It would be nice, as some of you are thinking, if I could just copy and paste. But I'm using this program called MyPaint. It's available also in Windows, and it's in Mac, and it's in Linux, what I'm using. It's really basic. It loads up really fast. It doesn't take up a lot of system resources, and I don't have a lot of options, and the copy and paste is not very good. It's my one criticism of it. It's one feature I would like to have, but it's so resource friendly that it's fast. The Windows version is not. The Linux version is. I don't know about the Mac. So let's go about solving this. The easiest way to solve this is we're going to isolate the middle term to have just the x term. So that means I'm going to subtract minus 1 from all three parts. Yeah, that's a legal operation. We can subtract it from all three parts. You have to remember to subtract it from all three parts. By parts, I mean this is the first part of the inequality, the minus 7. This is the second part, and this is the third. So minus 7 minus 1 gives me minus 8. 2x plus 1 minus 1 leaves me with 2x. That's the whole purpose of subtracting minus 1. And 7 minus 1 is 6. So now I want to just get a single x. So again, we have to be careful. X, the coefficient of x, is positive. So I can divide through all three parts by 2. And I get minus 8 divided by 2 is minus 4. 2x divided by 2 is x. And 6 divided by 2 is 3. So I can immediately write this in interval notation. The values of x are greater than minus 4 but don't include minus 4, and less than 3 but do not include 3. What would happen if this were a negative sign? I don't think there's an example that I'm going to give you. So let's just go right down here and pretend that we have minus x. We have a different problem altogether. Is less than minus 2x is less than 6. So what we have to do is multiply all three parts by minus 1. We're multiplying by a minus 1, so that requires that we flip the direction of the inequality symbols. So as a result, we would want to rewrite this as minus 6 is less than 2x is less than 8. So if you think about it, what you would do is you can figure out whatever rule you want. One rule is, well, you change the sign. If you multiply all three sides by a negative, the sign of the middle term goes positive, but the 8 moves to the far end and becomes positive, and the 6 moves to the other end and becomes negative. That's an easy rule. But of course, this is not our problem. Double entendre, meaning it's not the problem given us. I have a feeling you may get one of those problems in your homework. That's the reason I wanted to do that. And if you think about it, the solution set is going to be minus 3 and 4. So the solution set, if you want to remember a rule, if I get the solution set for this but rather had this, they just flip. The 3 moves over and becomes minus 3. The 4 exchanges 3 and becomes plus 4. But I think in general, the best thing to do if you're given a problem where you have a negative coefficient on the x term is you just go ahead and work it out until you get to this step right here, and then multiply everything through by minus 1, and then just reread it. This says 2x is greater than minus 6, which is what this says right here. 2x is greater than minus 6, and 2x is less than 8. And that's what this part says right here. 2x is less than 8, and rewrite it in standard form. It's always good because our number line, when we think about our number line, the natural ordering is this way. If A is up here and B is down here, then B is less than A. So that's kind of the reason whenever I do things involving inequalities, I try to rewrite them with the equal sign this direction, or the inequality this direction, because then it's natural to invoke the visualization of the number line. Okay, so let's do number B. Now number B is has to do with what am I trying to do right here? Number B has to do with row 4. So you might want to bring up row 4. So in this case, the absolute value, this is 2b, the absolute value of 2x plus 1 is stated to be greater than 7. So that means 2x plus 1 is greater than 7, or 2x plus 1 is less than minus 7. Now if you look in the actual ordering of the way I have it written out in row number 3, I have 2x plus 1 is less than minus 7, or 2x plus 1 is, that's wrong right there. I said one thing and wrote the wrong inequality. I'm glad I reviewed that. There we go. If it will write, or 2x plus 1 is greater than 7. I'm glad I caught that. So literally this was exactly what I was having in mind. When I was writing this down, I literally had this view right here, and here's my 7, and here's my minus 7, and my algebraic expression is 2x plus 1. It doesn't include 7, but it goes on to infinity. It doesn't include minus 7. It goes on to infinity. So 2x plus 1 is less than minus 7, or 2x plus 1 values are greater than 7. So let's go ahead and solve these. So 2x plus 1 is less than minus 7. That gives me 2x. I'm going to subtract minus 1 from both sides. So that gives me 2x is less than minus 8. Now let's divide both sides by 2. So that gives me x is less than minus 4. Or 2x is greater than, I'm going to subtract 1 from both sides. 2x is greater than 6. Divide both sides by 2. So x is greater than 3. So this interval here, x is less than minus 4. So x starts at minus infinity, and it gets right up to 4, but does not include it. Here, x is greater than 3, or if you want to write it the other way, 3 is less than x. That means it includes 3, and all values, it does not include 3, and all values greater than 3, but I've got to take their union. So let's see what the union will look like. Is there any simplification of the union? So let's do my two number lines here. Number line 1 and number line 2. They won't be parallel, I can almost guarantee you right now. So all I need is to place 3 on one of them and 4 on the other. I'm going to change to maybe yellow, and let's express this one on the top number line. If you want, you can remind yourself that this goes to infinity and this goes to negative infinity. So let's express the interval minus infinity to 4. Well, 4 is not included, but anything less than 4 is. Let's express this interval. Well, 3 is not included, but anything greater than 3 is. So as it turns out, when I take the intersection of those two sets, the resulting set is any area of the number line that it has at least one squiggly yellow line. But there is never any area of the number line that doesn't have at least one squiggly line on the above line or the below line. So the actual union of those two sets is the set that starts out with minus infinity. I've got a squiggly line at least in one line. I've got squiggly lines in both lines, so it's still there. And I've got squiggly lines at least in one line, so it goes on from minus infinity to infinity. That means all real numbers. So this is what my math lab is going to require you to write, and that's what I want to see too. So you can simplify sets just like you can simplify algebraic expressions. You've just not had as much practice doing so. And that's the reason I drew this visual help aid, so you could do it. Others can do it in your head because you can visualize what this is, and you can visualize what this is, and you can realize that otherwise you can do this. Now you can't always, now here's the thing, you can't always simplify the union of two sets to a single interval, the union of two intervals to a single interval. Sometimes this is as simple as it gets. In particular, if instead of 3 here, I had 5, I could not simplify it. So let's go on. So 2c. Oh, so do we do 2? Yeah, let's do 2c. We're ready for 2c. So here I'm going to show you a beautiful thing. Math is aesthetically beautiful to me, not only conceptually, intellectually, in the form of concepts is it beautiful, in the form of proofs is it beautiful, but it also can produce some beautiful images. This is just a beautiful instance of reasoning. So this is 2c. So we're going to solve this by just thinking about it. So we're going to have the absolute value of 2 minus 5x is greater than or equal to minus 4. Well, I take that back. This is not the one that we can solve that way, but we're still going to solve that. So if you remember, if we have the absolute value of x is greater than, okay, it's the next one, I'm sorry, we'll do 2d that way. The absolute value of x is greater than k, translates to or is equivalent to x is less than minus k, or x is greater than k. In this case, k is equal to minus 4. And my x here stands for this algebraic expression. So let's rewrite this. So 2 minus 5x is less than minus k. So minus k is minus 4. So it's less than 4. And over here, I have x is greater than k, so my x stands for 2 minus 5x. It stands for that unknown value is greater than, k here is minus 4. So we're done. We've translated it to an equivalent form. And now let's solve it. So remember from my last lecture, I like my coefficients on my variable term to be positive. So I'm going to subtract 4 from both sides and add 5x to both sides. In other words, I moved my 4 to the left-hand side, it became negative, and I moved my minus 5x to the right-hand side to get it to become positive. So this gives me minus 2 is less than 5x. Now I can divide through by 5, and I don't have to worry about flipping the sign. So minus 2/5 is less than x. So I've got one part done. Now I have to do the same thing over here. I'm going to do the same trick. I'm going to move the minus 4 over. It becomes plus 4. And it's greater than 5x. So that gives me 6 is greater than 5x. My coefficient on the x term is positive. So I can divide through by 5. So 6/5 is greater than x. So now what I have to do is I have to write this in interval notation. So OR denotes union. So our first step can be I'm going to suggest you write this as its equivalent form. So remember, I have the inequalities facing both directions. So that makes it easy now that they're facing both directions. So this says x is greater than minus 2/5. Minus 2/5 is not included, but it's all values of x that are greater than minus 2/5. And over here, x is less than 6/5, and 6/5 is not included. So again, this OR translates to the union. I'm going to take the union of these two sets. So we'll just do it visually. Visually is a good way to do it. So I'm going to write one number line, the other number line, and all I have to do, I don't have to worry about where 0 is. I'm just going to simply say that's going to represent minus 2/5, and this is going to represent 6/5. Now it is important that the inequality that you get minus 2/5 is to the left of 6/5. And it's easy in this case, we don't have to do anything with converting them to decimals to check, because this is negative and this is positive. Positive is going to be to the right. So let's write the interval here on the top line. So minus 2/5 is not included, but anything above or greater than 2/5 is. Here, 6/5 is not included, but anything below 6/5 is as well. So again, our final answer is, when I take the union of these, is minus infinity to infinity. Okay, so an easy check. So let's do number D. So we'll use reasoning when we get to number E. Well, oh, there she is. So number D is a lot of problems here. It's the same type. 2 minus 7x minus 1 is greater than 4. So if you look at the fourth row, the 2 minus 7x is our unknown quantity. But what I need to do is simplify this over here. So what I'm going to do is I'm just going to add 1 to both sides. So this is equivalent to 2 minus 7x in absolute value. I'm adding 1 to both sides. So when I add 1 to both sides, 4 plus 1 is 5. So in this case, I have, remember, the absolute value of x. Here x just stands for this polynomial is greater than k, implies that x is less than minus k, or x is greater than k. In this case, k is equal to 5. So let's go ahead and solve this. So that tells me 2 minus 7x is less than, minus k is minus 5, or 2 minus 7x is greater than 5. This is literally the visualization from the very first part. So again, I'm going to move the minus 5 over and it's going to become a plus 5. And I'm going to move the minus 7x over to give me 7x. That was nice. So 2 plus 5 is 7. And that's 7x. I'm going to divide both sides by 7. So I get 1 is less than x. Or, remember this is an or. Over here I'm going to do the same thing. I'm going to move the 5 over. And it becomes minus 5. And the minus 7x becomes 7x. So 2 minus 5 is minus 3 is greater than 7x. So minus 3 divided by 7 is greater than x. So we're taking the union of two intervals. So x is greater than 1. 1 is not included. But all numbers greater than 1 is. Over here, I'm going to rewrite that. X is less than minus 3/7. I just find it easier to have the inequalities on both directions. So in this case, minus 3/7 is the largest value, and anything less than minus 3/7 is included. So we're taking the union of these two sets. Again, I'll just do it this way really fast. We can really make it go quick. Now I'm just going to go to freehand. This is 1, and this is minus 3/7. Here, for this set, it's all numbers less than minus 3/7, all the way to minus infinity. Here, it's all numbers greater than, not including though, 1 all the way to infinity. So the union actually is missing this middle part. There's part of the number line that is empty in both the top and the bottom. So there is no simplification. So literally, the answer can only be expressed this way. The values of x that make this a true inequality are contained in the union of 1 to infinity with minus infinity to minus 3/7. And it doesn't matter if you put this set first or this set first. My math lab may make you do it, and that's bad technique, because the union of any two sets, the union of A with B, is exactly the same. These two sets are this, not B, A. Those two sets are exactly the same. So let's do number E. Now number E is one we can do by just applying mathematical reasoning. Can't see my top bar hardly. Oh, right there we go. So this is 2e. So I have the absolute value of 4x minus 7 is less than minus 3. So what the heck? Let's reason. Let's think about this. What do I know about the value over here? No matter what value of x is chosen, when I multiply it by 4 and subtract 7, I'm going to take its absolute value. That's the last operation. And the absolute value of any number is greater than or equal to 0. So what I know is the absolute value of any number, by its very definition, is greater than or equal to 0. So whatever this happens to be, on the left-hand side, it's going to be in this part of the number sign. And that is never less than minus 3. This part of the number line is never this part of the number line. So just by reasoning, a number that is greater than or equal to 0 can never be less than 3. There are no shared elements in those two intervals. So the answer is, in English, no real number. Or, in set notation, it's the empty set, which we denote as a 0 with a slash through it. Super simple. And the next one here is just really simple. Notice this is not an inequality, it's an equation. So I'm not going to work it out for you, but you will use just simply the first row, where our unknown quantity in this case is 5x plus 15. So we're going to use the property that the only number whose absolute value for the absolute value of a number is equal to always just a single number. That's what I'm trying to say. So all I have to do is 5x plus 15 is equal to 0, because minus 0, this is what I'm trying to say, is equal to 0. 0 is the only number for which this is true. For any other number a, minus a is not equal to a as long as a is not 0. But as soon as a becomes 0, that's the exception to the rule, and minus 0 is equal to 0. So I literally only have to solve this linear equation, and you should immediately get 5x is equal to minus 15, x is equal to minus 3. So our set contains one element, not two. Okay. So here we have another interesting concept. If you're into engineering or any type of machine work, we have the concept of tolerance. And that's where this is going to come into play. But let's first look at this visually. So another concept, which we actually saw visually, is the undirected distance. Say, wait, what do you mean an undirected distance? Well, I can walk west 5 miles, that's a directed distance. And I can walk south 5 miles, that's a directed distance. My destination is going to be different in each case, but the distance I traveled is going to be the same. So the undirected distance, it's just the distance traveled between 2 points A and B, is given by, take your pick, A minus B or B minus A. It does not matter. They are exactly the same. So we're going to use that fact in solving problems. So we're going to write each statement as an absolute value inequality. I'm going to pretend this is 3a. I don't know what number we're on. K is no less than 5 units from 8. So let's draw our number line here. I'm not going to freehand it. Here's my number line. And I will freehand this part. So this is 8. So we have some value K that is no less than 5 units from 8. So that means if I go out, that's 5 units. that this interval here cannot contain k. So this is 5 units. The distance from here to here is 5 units, and the distance from here to here is 5 units. So what does that tell you? So it's okay, so that means it's okay for k to be there. That's an acceptable value of k. Or k to be here. So if k is either in this area or in this area, it is no less than 5 units from 8. So that means k, if I subtract k minus 8, in absolute value, it's going to be greater than or equal to 5. That was the whole reason I wrote this out visually. So if I take any number up here and subtract 8 from it, it will be either greater than or equal to, I guess k is included. If I've got the equal sign here, k can actually be there. Yeah, so k can include 5. So notice that I used the blue rather than the red, because 5 is always less than. So that's kind of a weird conceptual thing, and I don't know any other way than you'll have to think this one. Think it through. And you can use this drawing and this whole explanation as a paradigm. So let's do the next one. 3b, because we're writing each statement as an absolute value inequality. So we'll try to kind of, when we're doing this, we're going to try to maybe work out and speak about what we're doing here. So n is within, that means the range is 0.0001 unit of 6. So from 8, notice, 8 was on my number line. Now we have unit of 6. So what I'm going to write, and I'm just going to write it right here, right in the middle, that is 6. And our variable here is n. So n is within 0.00, this is tenths, hundreds, thousandths, 1/1000th unit of 6. That means I can start at 6 and I can move out a distance in either direction of 0.001. But I can't actually get to that point, right? Because it's within. It doesn't include, it's within. So all of my n values can be in here. So that means if I subtract n, if I subtract from any value of n, if I subtract 6 from it, I'm going to be less than this distance. So, okay, let me do it. So I said n is in this area. So let's say n is right here. This is my n. So if I subtract 6 6 from n in absolute value, it's going to be less than the length in yellow. So I hope that helps. So this is n is within 0.001 unit of 6. Sorry to write it in red, but that's what you got. So finally down here, we have number 6. Don't worry, let's figure this one out. We're going to be using exactly what I said, or taught, or did. Get rid of that. Get a color that we like. In quality control in manufacturing, we often want to keep the difference between two quantities within some predetermined amount called the tolerance. Now, we live on the Space Coast, and I would, if any of you know any NASA engineers, could you ask them what type of tolerances they have to deal with in making spacecraft parts, and email me? I'm curious about that. I would say those tolerances are really, really small. So suppose that y is equal to 2x plus 1, and we want y to be within 0.001 unit of 4. So from what we just said, what values of x will make this true? So literally from problem B, we have y, y minus 4 has to be less than 0.01. But y is given to be 2x plus 1. So let's replace y with 2x plus 1. We're still subtracting 4 from it, and it has to be less than 0.01. Now, if you want to write 0.01, so that's tenths, that's 100ths, recall 1/100th is equal to 0.01. If you were in the classroom and where you can't use calculators, that would be an important move in solving this. Let's go ahead and simplify this out all the way. So this is 2x minus 3 is less than 1/100th. So what does that mean? 2x minus 3 is less than 1/100th, is between 1/100th and minus 1/100th. This is the third row inequality. Now, I'm doing this purposely because the first thing I'm going to do to solve this inequality here is I'm going to clear the denominators, because I'm pretending that this is my face-to-face class where you can't use calculators. I know you just want to grab a calculator, but we're not. So I'm going to multiply. I'm going to clear the denominators. So I'm going to multiply all three parts by 1,000. So when I multiply this first part by 1,000, I get minus 1. I'm going to multiply the entire middle part. I said 1,000. I mean to say 100. And I'm going to multiply the last part by 100 as well. And that's going to give me 1. So now I'm going to simplify. So this is minus 1. 100 times 2x is 200x. 100 times minus 3 is minus 300. So now I'm going to add 300 to all three parts. Minus 1 plus 300 is less than 200x. Minus 300 plus 300 is less than, I'm adding 300 to all three sides. So minus 1 plus 300 is 299, is less than 200x, is less than 301. And now all I want him to do is simply say x is, I'm going to divide all three parts by 200. So x is between 299 divided by 200, or 301 divided by 200. And if you want to know what those numbers are, you can, in decimal form, you can write it out. But if you can think about it here, we've got the common denominator. So that already tells you that x is within 1/100th of these two numbers. It tells you right here. So at any rate, one last question. Yeah, one last question. We have mathematical reasoning. So I want you to consider, let A be any real number. And consider the value of A times X, where A and X are real numbers. So here's my question I'm posing to you. For which values of A do we have the absolute value of A times X is equal to A times the absolute value of X? So what I've done here is I just said, oh, if I have the absolute value of A times X, sometimes I can just take the A and move it on the outside of the absolute value signs. Which values of A allow me to do that? Every single real number A, just a few A's, no A's. Start with what you know must be the case for the absolute value of A times X. That follows from the definition of the absolute value, and see if you can't come up with the answer to that. You might or you might not see that on our exam. So this concludes lecture 8.1.8.